Hey guys, it's Off by One here, and today we're going to be solving reverse bits. So in this problem, we're told that we're giving a 32-bit unsigned integer, and here are just some notes that aren't really relevant to us right now because we're not coding in Java. So basically what they're asking us is, let's say we're giving a number 1100. What they want us to return is the reverse of these bits, so we would return 0011. So just to clarify, this number here would be a 12, and this number here would be a 3. And there doesn't really seem to be any kind of special relationship between these numbers. So the only way to really solve this is by using our logical operators and doing bit manipulation. So I'm going to show you how to do that. So here I've written the example we're going to use for this problem, and I chose to use 7. And I'm representing it using 4 bits because the solution should work regardless of how many bits there are. And using 4 here for our example just makes things a lot easier to write out. So let's see. To reverse this, we expect the 1 over here because that's the first bit. The second bit is going to be 1, so we want a 1 over here. And then this bit is also a 1, so we want a 1 there. And then the 0 goes at the end here. So that's obviously pretty simple, but how do we get to the solution? Let me do it again, but this time I'm going to show you a little more of the process. So first we wanted to check the rightmost bit. So how do we do that? Well, if you've seen other types of problems like this, you'll know that we can use AND 1 to see what our last bit should be. So for example, if we do 0, 1, 1, 1, and then with 1, our result is just going to be 1. So that tells us that our last bit is a 1. So we can make a new integer, and we can just call it result. And for now, we can just make it equal to 1. Okay, so how do we get to the next bit? Well, we could just get rid of this 1 by shifting everything to the right. So now our new value is going to be 0, 1, 1. And if we AND that with 1 again, we'll see that this bit here is a 1. But how do we include that in our result? Well, if we do result is equal to 1 and we leave an empty space here, then we can use that empty space to put the result of this operation here, which would be a 1. So I would insert the 1 here. Now I'm going to do that again. So we get rid of this bit now because we already saw it, and we shift it again to the right. So now our number is going to be 0, 1, and we AND that with 1. And now we rewrite our result. So result is going to be 1, 1 with an empty space here. And you see that the operation is going to give us a 1. So we insert a 1 there. And then now we're almost done. We just have to shift it again to the right one more time. So now we're just left with 0, and we AND that with 1, and then we get a 0. So now our result is going to be 1, 1, 1 with an empty space for the 0 here, which is like this. So I know I went through that pretty fast, so now I'm going to write each step and go through it one by one. So the first thing we did was initialize this result variable. So once we have that, all we have to do is keep shifting it to the left to make space for the newest bit. So we can say that we initialize result, and then we shift to the left. And then once our result variable is shifted to the left, then that means we have space to write the newest bit in. And the way to check what the newest bit would be is to do this operation here where we AND our n by 1. So we can say we AND n by 1. And the result of ANDing n by 1 is going to be our least significant bit. So it's always going to be the rightmost bit. And once we have that result, what do we want to do with it? Well, we want to insert it here at result. But how do we do that? Well, since we're only ever inserting a bit to this point here, which is the rightmost bit, it's always going to be equal to 1. So we could just add the result of this to our result variable. So for example, let's say result is equal to 1, 0. Well, if the AND gives us a 0, then we're still good here. We can just add 0 anyways, and nothing will happen. It'll stay as 1, 0. But if we add a 1, it would change to 1, 1. And that's the behavior we want. So for our next step, we could just say that we want to add the result of step 3 to our result variable. And then at the end, all we want to do is shift n to the right by 1 to get rid of the rightmost bit. So that way we can look at the next bit. So we can say shift n to the right. And that's our whole algorithm. So I'm going to redo this problem, but I'm going to show you each and every step one by one to make sure you understand. So our first step is going to be to initialize result. So we're going to initialize result to 0. And now we shift result to the left. So we're going to have result is equal to 0, 0. Okay, now we go to this third step where we AND n by 1. So our n is currently 0, 1, 1, 1. And if we AND that with 1, we're going to get a 1 because these two bits are 1 and the rest are going to 0 out. So now our result of this is 1 and we want to add it to the result. So we're going to have result is equal to result plus 1 because we had a 1 here. So now our result is going to be 0, 1. And then we're told that we have to shift n to the right. So basically this number is gone. So now our n is going to be equal to 0, 1, 1. And that would be the end of our first iteration. And we have to do this 32 times because we're told that n is supposed to be a 32-bit integer. So that's why we're doing it 32 times. And then at the end, our result variable should have our reverse number. So we would just return result at the end. Our time complexity for this algorithm is going to be O of 32, which simplifies to just constant time because our worst case scenario is still just a constant. And for space, we're using constant space as well. The only thing we have is this variable here, and that takes constant space. So now let's get into the code. So to start, I'm going to initialize the result variable, and that's going to be set to 0. And now we do a for loop 32 times. So for I in range of 32, and that should give us 32 iterations. We want to start by making space for the new bit that we're going to add. So result is going to be shifted to the left by 1 bit. Now what we want to do is AND n and 1, and then get the result from this, and then append that to our result at the end. So we could say result is equal to result plus whatever the value of this would be. If it's 0, it doesn't matter because it already is a 0 anyways. And then at the end, we want to shift n to the right by 1 to get rid of the newest bit. So n would equal that now. And then at the end, we can just return our result. Also, instead of plus here, you could do OR. It's a little fancier, but it still works all the same. Doesn't really matter what you use, but I think it looks cooler like that. So I'm going to submit the code like that. So as you can see, this code is fairly efficient, and now I'll go through the code manually. So for this example, I'm going to use n equals 4, and the binary representation for that is 1, 0, 0. So to start, we want to set our result equal to 0, which I've already done here. So now we want to iterate 32 times, and obviously I'm not going to do that here because that would just take way too long. So let's start with our iteration of I equals 0. What do we do there? Well, we start by shifting result to the left by 1. So now our new result is going to be 0, 0, which is still 0. And now we want to AND n in 1. So n is currently 1, 0, 0. And if we AND that with a 1, then we get a 0. So from here, we add this 0 to our result. So it's already 0, 0, so I'm not going to change it. And now we shift n to the right by 1. So now our new binary representation is going to be 1, 0, because we got rid of this 0 here. So now we go to our next iteration, which is I equals 1. And the first thing we do is shift result to the left by 1. So now we're going to have 0, 0, and 0. And now we want to AND n by 1. So our new n is going to be 1, 0. If we AND that with 1, we get a 0 still, because 0 ANDed with 1 is 0 still. And we add that to the result. And it's already 0, so I'm not going to update it again. And now we shift n to the right by 1. So our n is now just going to be a 1, meaning we got rid of the 0. So now we go to our last iteration, which is I equals 2. And the first thing we do again is shift result to the left by 1. So now we're going to have 0, 0, 0, 0. And from here, we want to AND n and 1. So n is currently 1. And if we AND that with 1, we get a 1. So now we add this to the result. So the result is going to be all of these zeros plus 1, which would equal 0, 0, 0, 1. And then at the end, we shift n to the right by 1. So that would just make it 0 since there are no more bits left. And we can just say our for loop ends there, and we return our result. So our result is just 1. Like, all these extra bits don't matter. And our result is correct, because as we can see here, 1, 0, 0 reversed is just 0, 0, 1. And that's correct. If this video helped you in any way, please leave a like and subscribe. Thanks for watching, and I'll see you in the next video.